Hello everyone. In this video, we introduce Interpretable Motion-Attentive Maps, or IMAP, a CVPR 2026 paper on interpreting video diffusion transformers. Video diffusion transformers can generate realistic videos from text prompts. However, it is still difficult to understand which internal features are responsible for specific objects, events, or motions in the generated video. Most existing interpretation methods focus on object localization. But in video generation, many important errors are related to motion. For example, the wrong object may move, the timing may be incorrect, or the motion may be physically implausible. So this work moves beyond object-centric interpretation toward motion-aware interpretation. The core idea is to produce saliency maps for both objects and motions. So our goal is to locate concepts, such as alpaca or running, both spatially and temporally within video DITs. We start by looking inside a video DIT. A video DIT receives a text prompt and video latents, and then generates video frames through repeated transformer blocks. So to explain the generated video, we first inspect which internal features contribute to the generation process. First, a video DIT is not a single block. It consists of many repeated DIT blocks, and not every layer is equally useful for interpretation. Some layers contain low-level or noisy features, while others contain clearer semantic information. So before constructing a saliency map, we need to decide which layer to analyze. To select informative layers, we treat the attention matrix as a transition matrix in a discrete time Markov chain. From this perspective, the second largest eigenvalue tells us how meaningful the transitions are. So we use lambda 2 as our layer selection criterion. Empirically, we show that DTMC-based lambda 2 indicates the semantic interpretability of layer features. In other words, layers with higher lambda 2 produce more accurate feature maps. Based on this, we use lambda 2 to select layers inside the video DIT. After selecting the layer, we connect text concepts with visual features. For this, we use query key matching. Specifically, we measure the similarity between visual queries and text keys inside the multimodal attention mechanism. We observe that query key matching provides accurate concept localization. Even when the full attention map is not perfect, the strongest match visual token often corresponds to the target concept. We call this the text surrogate visual token. So, given a target word, query key matching gives us its text surrogate visual token. Then, to build a dense saliency map, we use the similarity between visual tokens. First, we compute the visual token self-similarity matrix, which is equivalent to a gram matrix. Next, we take the column corresponding to the text surrogate visual token. This column becomes a saliency map over visual tokens, which we call gram-col. In short, gram-col localizes a concept by measuring visual token self-similarity around the text surrogate token. Gram-col provides a strong concept localization map, but by itself, it has some limitations for motion localization. Previous studies suggest that different attention heads can play different roles. Based on this, we identify which heads are responsible for capturing motion. Our key assumption is that if an attention head captures temporal information, then its features should be separable across frames. In other words, features from different frames should form distinguishable groups. To measure this, we compute a frame-wise feature separation score. Experimentally, heads with higher separation scores tend to perform better in motion localization. This supports the idea that frame-wise separability is closely related to temporal responsibility. Based on this, we introduce a top K-based motion head selection algorithm. This allows our method to filter video DIT features before constructing the motion saliency map. In summary, our method first selects informative layers. Then, it finds the text surrogate visual token using query key matching. Next, it computes gram-col using only the selected motion-related heads. The resulting motion saliency map is called the Interpretable Motion-Attentive Map, or IMAP. The experiments show that IMAP outperforms existing baselines both qualitatively and quantitatively. IMAP can also be applied across multiple video DITs. The experiments show that IMAP outperforms existing baselines both qualitatively and quantitatively. IMAP can also be applied across multiple video DITs. Additionally, we analyze feature similar but conceptually different cases. IMAP precisely captures the object that actually performs the motion, showing its advantage over appearance-only localization. To summarize, Video DITs contain interpretable concept features. Motion-related heads can be identified through frame-wise feature separation, and IMAP provides a simple, training-free way to localize motion concepts in both space and time. Thank you for watching.